Hello and welcome to this video. We are going to be discussing polynomial graphing and factors and zeros. In part one, we are going to be looking at the connections between factors and zeros when it comes to those polynomial graphs. By the end of this first part, we're looking to be able to find the zeros of a function from its factored form and kind of look at how that factored form affects what the graph itself will look like. So we now are looking at three different graphs with their functions to go along with it. So I want you guys to think on your own as you're watching this and looking at graph number 1, number 2, and number 3, and think about what you notice or wonder about any of these three graphs or functions that we look at in front of you. No real wrong or right answer here. We're just looking for observations, and you'll have a way to state those observations after you kind of finish looking at these. So take a little bit to look at all three of these. Just some quick observation on things you might notice. They kind of point, the arrows in both directions point down and then up for all three of these, so they have that in common. They all have three x-intercepts and only one y-intercept. They have that in common. And they also all have three factors, 1, 2, 3 factors for all of these functions. And you might have some different observations or things you might wonder about after you've thought about these three functions and graphs too. So in this slide here, we have some different examples of the factored version of a bunch of polynomials. And a lot of these kind of work in the same way. So we're going to kind of do a couple of these. So as we go through it, you should maybe pause the video now to see what x values would make this true. So then we'll do a couple of them together as well. So for starters, in number 1, we should note that these all have three factors. So if you are trying to make the equation true and have it equal 0, since this is all multiplication, each one of these different parentheses could equal 0. And if that's the case, the whole thing would end up being equal to 0. And so for this particular problem, number 1, I can find three different x values that would make the whole function equal to 0. So the first one would be -4. So if I put in -4 into all those x's, I would have -4 plus 4. And then I would have -4 plus 2. And I would have -4 minus 1. And in theory, all of that should be equal to 0. Now, these second two parentheses, well, that would be -2, and this one over here would be -5. So -2 times -5 would be positive 10. But then this first one, -4 plus 4, ends up being equal to 0. So we figured out that one value was -4. So if we kind of get rid of that and start over here, you basically are going to do that with each of these parentheses. Whatever makes each one of these parentheses equal to 0, well, that would mean that the x value would be the one we're looking for. So we already figured out that x equals -4 would work for this one. So if we look at just that second parentheses, if we take what's inside of it and set it equal to 0, well, I would see, well, x is going to have to be -2. And if I put -2 into this middle parentheses, that would make that one 0. And then I could look at the last parentheses. And so I have x minus 1 equals 0. And that's for this one. Well, that means that x is going to have to be equal to 1. So it turns out that -2, 1, and then the -4 we had before are the three values that would make number 1 equal to 0. That is going to be very similar to number, let's mark these. So if you kind of look at number 2 and number 4, those are both pretty similar to the one we just did. And you might want to pause the video and try those out. For instance, they would have, this one, number 2, would have the same ones, but since x minus 3 is on the end there, that would mean that 3 is another number that would make this last parentheses equal to 0. Some other ones we want to point out is number 3. We have parentheses that have been squared here. So we've talked about parentheses in general before, in that when you have a parentheses squared, just remember that you're doing like x plus 4 parentheses squared means that you're doing x plus 4 times itself. So we have that times another x plus 4. And then you have 2x plus 2's. So if we have those all kind of expanded out like that, just like we did before, we can set each of these equal to 0. So we would have x plus 4 equals 0. And we have x plus 2 equals 0. And so that would just mean that for number 4 here, we would have x equal to negative 4 as an answer, and x equal to negative 2 as an answer. And the negative 2 in the front is not going to affect this because there's no x to put in with this negative 2 right here. So in number 4, it's kind of just the same thing as the previous problems. And same thing with some of these other ones that we can look at real quick. So for number 5, for instance, we can still make each one of these 3 parentheses. We can set it equal to 0. So for instance, I could take 7x minus 3 and have that equal 0. And so I just need to do a little bit of solving equations and see that x is going to end up being equal to 3/7, which you could turn into a decimal if you prefer that. So you can see decimals down here. And then that's one of those x's. So you would find out, well, from x minus 10, you would know that one of the x's is also a 10, a positive 10. And then 2x plus 8, you would do the other part. 2x plus 8 equal to 0. And if you solved that for x, you'd end up with negative 4 as one other answer. And you can always check that by putting your x in. 2 times negative 4 plus 8 would equal 0. So another one there that made the whole thing equal 0. So otherwise, number 7, kind of the same thing. And then we have the last ones of 6 and 8 that we're going to talk about. So for number 6, we have something that's written in standard form. And we would want to factor that quadratic. So think back to your factoring skills. That would factor into x minus 4, or x plus 4, I mean, and then x minus 1. So you would kind of figure that out first. And then you would see, well, I'm looking at x plus 4 and x minus 1. So the two x's that would make this all 0 would be negative 4 and positive 1. Now, the last one is number 8. It's a little weird, but we can still use the same strategy. Set whatever is inside the parentheses equal to 0. And just solve for x. So we use a little bit of our quadratic equation solving skills, and we would figure out that x squared equals 4 means that negative 2 and positive 2 would both be answers, since you could put either of them into x squared and then subtract 4 to get 0. And then the x plus 9 part would just tell me that x equals negative 9 would also be one of those numbers as well. Essentially, this strategy is to look at each factor and set each factor independently equal to 0 and solve for x. Your answer would be a number that would make the whole thing 0, since it's all multiplication. And you can apply that rule to all 8 of these problems. So moving to our next part. So if you were in class, we're going to be doing a matching activity, and I will show you guys, and I will post the cards that you're going to be matching. But basically, you're just trying to match an equation with a graph and use what we've talked about as far as kind of looking for explanations of why you think one matches the other. And we're trying not to get too in depth with zeros and factors yet. You're just using your skills you already know about graphing to kind of match them up. So let's kind of just look at one matching card part together right now. So for instance, in card A right here, we have x minus 5, x minus 4, and 2x plus 3. So you could kind of graph that and try to match it up. But something to remember is that we have x minus 5, x minus 4, and 2x plus 3. So using our strategy from the last slide, we'd be looking for a polynomial with our zeros as 5, 4, and then negative 3 halves. And then you would just be kind of scrolling through these and looking for where you have these three numbers as your x-intercepts. So if that's close, 5, negative 4, and negative 3 halves, that's close to what we have. And you can kind of explore through that. So like this one, 4, 5, and negative 3 halves would match this right here. So card A ends up matching card 4. But this is something you can explore on your own with the what I will post in Google Classroom for you guys. And we can move to our next slide now. So to kind of wrap this up, I'm just going to kind of explain how you identify what values of x make v of x equal 0. So something important here, when it says make v of x equal 0, the values of x that equal 0, that is when you have x-intercepts, or when y is 0, since this is basically equal to y. So just remember that x-intercepts happen when y is 0. So any x value that makes this whole thing equal 0, those x's are going to be the ones that are going to be your x-intercepts because they make y 0. And we're using the same strategy as well for doing 11, for figuring out each of these three parentheses. So we are going to set what's inside of each factor equal to 0 and solve for x. So we would have 11 minus 2x equal to 0. And that means that x is going to be equal to, looks like 11 halves. Positive 11 halves. And then we have 8.5 minus 2x. We can set that equal to 0. And that means that we would have an x value there. So if we added 2x, we would just be doing, or no, we have an extra x there. So we would just need to do that quick division there. So we would just be doing 8.5 divided by 2 and getting 4.25. And then the last one, something to look out for, when you just have x as a factor, that means that this x right here is just going to be 0 automatically. And that's something to remember for future problems. And that's how you would kind of find all the values when y is 0 or v of x equals 0. And just remember that all those x's you're finding, those are your x-intercepts, or your zeros in the way of saying it. And so now we have a kind of a wrap-up problem you guys are going to try on your own in a second, but just kind of read through it together. Polynomial y equals x minus 5 times x minus 2 times 4x plus 3 has been graphed incorrectly. Identify the error and how to fix the graph. So take a moment to try this problem out and see if you can find the error and how to fix it. So the error is they've kind of used the opposite signs of what you're supposed to. So from x minus 5, you would set that equal to 0 and figure out that your x-intercept is 5, and then you'd have 2, and then you'd have your last x as negative 3 over 4. So if you look at the graph, we have the exact opposite of that. We have negative 2, negative 5, and positive 3/4. So that's the danger you want to be careful of, is that when you see x minus 5, the minus 5 part is not the x-intercept. The 5 that would make this whole thing right here, this factor 0, is what you want to use instead. And that's something to be careful about. So this graph will kind of move so that we have these three x-intercepts I outlined above instead of the opposite sign ones we have in the problem below. And that is where we will end part 1 of this lesson. We are now looking at part 2 of our factors and zeros lesson. In this one, we will be looking at the different forms of polynomials and doing some relating between standard form and factored form, which you should remember from dealing with quadratics last semester as well. So by the end of this lesson, we're going to be trying to identify the features of polynomials and their graphs using both of those forms that I just mentioned. So take a moment to consider choices A through D here of which one of these functions does not belong with the other three. Now, there's no wrong answer or right answer here per se, but you can make a case for two different of them, I think. So one case you can make is that choice A is the only one in factored form. So that would be a way that it could be sticking out from the other three. That's one answer you could have thought of. Another answer is that choice D might be the one that is sticking out to you. Choices A, B, and C are all quadratics, which have degree 2. And if you multiplied out the factored form of choice A right here, that would end up being the quadratic as well. So that's kind of two different ways you could interpret this same problem here. We're going to be looking at a Desmos graph of this situation in a second, but let's kind of look through what is going on with it first. So for starters, we have f of x and g of x up at the top. They're both factored versions of a polynomial. And if you are looking at both of these in the same window, we're going to be looking at how the graphs are the same and how are they different. We're looking at also at rewriting them in standard form to see what kind of degree they have or what is the biggest exponent when you're in standard form. And then lastly, we'll look at h of x, and we're going to try to think about how h of x is going to be changing, and we're also going to look kind of a slider to go along with h of x as well. So let's, for starters, go to our Desmos page and look at number 1, and we're looking at f of x and g of x and seeing how different they are. So we have f of x in red and g of x in green, and we see our domain and range are set up. So if you're unsure how to do that in Desmos, what you can do, if you go down here to x-axis, you can kind of type in whatever you want to use. -10 to 10 and -100 to 100 is what we talked about before. And you can see that that is what our slide was talking about. So if you look at comparing and contrasting these graphs, so if we look at these graphs, well, we have so think about what you would say to that first. But if we were to discuss that right now, well, the red one we can see is kind of pointing down on the left and up on the right. Same goes for the green one. Secondly, well, we have a x-intercept here at -3, 2, and 7. So that makes a lot of sense. If you look at the factors and you think about what we discussed in part 1, well, the x-intercepts are our zeros from each of those factors would be -3, 2, and 7. So we have the 2 from this parentheses, and we have x plus 3, making -3 from this one, and then the +7 from the third parentheses. So that kind of finishes up how they're similar. So they also both have 3 factors total, 3 parentheses. We can see that they have different y-intercepts, 0, 21 and 0, 42. And we can see that their local minimums and maximums here at these points are local maximums, and then we have local minimums. Our green g of x has smaller values compared to our red f of x. Now, if we kind of skip to number 3, if we have h of x now, if you are changing the a value in the front, like if I changed it to 2, we can see that we are basically dilating these functions while keeping this x-intercepts the same. And that we're not changing what these factors are, we're just kind of multiplying out something through just kind of the first one. So if I made this into just a 2 right here, I could change that, get rid of that 2, and multiply it into the first part here, make it like that, and it's kind of the same thing. And we can kind of change it back to being the a value and kind of see how it ended up what we just looked at. So an a value in the front or an a value in one of these factors would cause it to dilate or flip upside down if you go to negative numbers, and you can see how it kind of dilates further and further as you go. So that dilation happens in polynomials just as it did with other types of functions that you've learned about in the past. Now, if we go back to our slides, number 2 asked, what degree do these polynomials have? Rewrite each expression in standard form. So we only really need to do one of them. So let's do that here. We can kind of multiply out these, and it depends on how you want to do it. Like you could just do arrows like x times x and x times 3, and then negative 2 times x and negative 2 times 3. So I would multiply these two parentheses together, and the answer that you should get after doing that is x squared plus 1x minus 6. And then we still have that being multiplied by x minus 7. So now we were doing 3 things times 2 things. You generally want to use kind of like the box area method to make it a little bit organized and a little bit easier to get right every time. But if you were to kind of go through that, so try multiplying these 3 times 2, and we'll go over the answer in just a few seconds. We now have the answer ends up being x cubed minus 6x squared minus 13x plus 42. So the degree of this particular polynomial would be a 3. You can see it's in standard form going from biggest exponent to no exponent at all. The biggest number would be a 3, and that makes it a cubic polynomial, which that is what you'd call a degree 3 polynomial. And the other g of x function would, since that has that 1/2 on the front, we basically could think of it as this whole answer being multiplied by 1/2. And then you kind of would just multiply across by 1/2. The degree itself would be the same, and that's why they have so many similarities to their graphs in general. So that kind of wraps up our spot the differences part of this lesson. So we can move forward. So some important things to note on this page here. So we have a factored form of this cubic polynomial, this degree 3 polynomial. So first question, where can you see the 240 in the factored form of the equation in the graph? So from standard form, we know that the last number right here is always the y-intercept, because x and x and x would be 0, leaving us 240. If you think about where that is in this factored form, if you multiplied out 4 by negative 6 and then multiply that by negative 10, you get positive 240. So those ending numbers in each factor would give you this, unless you have a number in the front, like if this was a 4 up here, well then you would do 4 times negative 6 times negative 10. Number 2 asks, which form do you think is better? I personally think that graphing something with factored form, especially polynomials, is much easier to do by hand and to understand what's happening in the graph. Standard form is really only easiest to see the y-intercept, which is not really that big of a deal. So I personally would say factored form, but that does not necessarily mean that would be what everyone would say. And then lastly, basically the g of x is a polynomial with the same zeros in degree with a vertical intercept or y-intercept of 120. So that would just mean that we have a kind of a value multiplied at the front, thinking back to an earlier slide. So g of x would be the same thing, but we would basically be multiplying by 1/2 at the front. And so that would mean that this y-intercept would be half as big, or 120, like you see right here. And that would be kind of the main things that, so some other things to note is that we're getting x-intercepts from each factor. So that negative 4 and then 3 and 10 are coming from each factor being set equal to 0. The y-intercept is whatever a value you have at the front, or if you don't have one at all, it's basically the second part of each factor being multiplied together to give you your y-intercept. And those are x-intercepts and y-intercepts are both very important when you're trying to sketch a graph or to understand what the graph might look like in general. And so last we have kind of an exit ticket sort of thing, a review problem of what we just covered. So we have a polynomial x plus 6 plus 3 and x minus 5. So why don't you take a second to answer number 1 and number 2, and we will look at those answers together in just a little bit. We have the answers now. So for number 1, if you multiply x plus 6 and x plus 3 together, you get x squared plus 9x plus 18. And then you're multiplying that answer by x minus 5 if you go left to right. And the answer you would have gotten from multiplying those together would be x cubed plus 4x squared minus 27x minus 90. And that would be the equivalent standard form polynomial to the factored one we started with, which was p of x. The degree of this blue standard form equation would be 3. It's written in standard form, so the highest exponent, it would be the 3 above the first x you see. The constant term is negative 90. And remember that negative 90 ends up being your y-intercept. And we got our x-intercepts from this function earlier. And that is going to complete our part 2 of our factors and zeros lesson. Next time in part 3, we're going to be looking at how we can use factors and zeros towards graphing and more further understanding of polynomials in general. Thank you for watching.